Hello, my name is Dan Ambray from Full Spectrum Diagnostics. Today we're going to look at the vibration fault periodic table. The periodic table is a logical visual mapping system to understanding vibration as more of a systems thinking. We start with the full table, 35 common rotating machinery faults. Our first step is to logically sort these faults for frequency content. This means we define how the fault relates to the shaft rotational speed. If the dominant response is at shaft turning speed, our fault is synchronous. If the response is an exact multiple of shaft speed, our fault is harmonic. If the dominant peak is less than shaft speed, it's subsynchronous. If the peak is not an exact multiple of shaft speed, it's not harmonic, it's non-synchronous. So it's the opposite of harmonic. They're not exact multiples of turning speed. And finally, if the spectrum is pulsating, it might be due to amplitude or frequency modulation. And this is the last group on the table. Our second sorting mechanism is the dominant directional response. The red blocks on the table indicate a radial fault, either horizontal or vertical. The yellow blocks are axial faults. The orange blocks can be radial or axial. And finally, we perform the recommended diagnostics indicated in the upper right-hand corner of each block. Our diagnostics are phase analysis, time waveform, orbit analysis, transient analysis, and ultrasonic analysis. Okay, 5 different possibilities to go down. So here we see a phase icon, here we see a time waveform, an orbit, a transient, and an ultrasonic. So they're different for different groups. So let's get started. And what we want to do is look at the faults and understand what's going on a little bit better. Our machine is a direct coupled pump. It's a 4-pole AC induction motor, no VFD. The turning speed is 1784. The motor has rolling element bearings as well as the pump, and the pump has 6 vanes in it. Okay, here's our monthly data. We take our route data in the positions 1, 2, 3, and 4, and we take axial, horizontal, and vertical at each location. So we're looking at 12 different measurements. We dump our data back into the database, and it compares it to an alarm criteria, which is this red line. And we're looking for anything that exceeds that red line. So I've already done a little of the work for you. There's a problem in the horizontal direction and the vertical direction at position 2. And it looks like there's a whole series of peaks. And the way I have them labeled, there's 1 times, 2 times, 3 times, 4 times. So they're appear to be harmonics. Okay, so we're going to take a little closer look at that. We go put our cursor on each one of these peaks. So I put my cursor on 1784. I divide it by turning speed, which is also 1784. That's my 1 times RPM. So that's turning speed. So it's a first multiple. I have another peak at 3568. Put my cursor on that, divide by 1784. It's twice running speed. Exactly 2 times. I have another peak at 7136, divided by running speed, it's 4 times. I have another peak at 6 times, which is 10,704 divided by 1784. I get exactly 6 times. So you get an idea. So we put our harmonic cursor on, which are all the boxes, and they all line up. Okay. If I want to look at them individually, I can put my regular cursor on there and then divide by whatever the running speed was, just like I did above here. On the vibration fault periodic table, we're going to look at the harmonic columns. And there are overlapping portions of this on each one of the groups. And we're going to be conservative and make sure that we grab all the harmonic information as well as the other faults that might be present. So we're a harmonic. We exact multiples of turning speed. That's one of the definitions that you see right here, exact multiple of turning speed. Okay, so everything else goes away except for my harmonic column and my natural frequency. My natural frequency is there because it can appear anywhere in the spectrum. It's related to mass and stiffness, not particularly to shaft speed. Okay. So we have a series of faults. We're going to take the next step and we're going to sort them by directional content. And right now we look at the axial response and nothing's in alarm. Horizontal and vertical both have alarms. There's some peaks being amplified, and there's a little bit of noise floor under here, if you see that. The noise floor is a good indicator of one of the faults on the table, and we'll get to that in a minute. But right now we're sorting by directional response, and axial isn't involved, so we can take all the axial faults off the table, which we've done here. So we got rid of the bent shaft, angular misalignment, cocked bearings. We can eliminate specific faults. This is gear mesh, blade pass, and rotor bar faults. So the gear mesh, first of all, we don't have a gearbox, so we can take that off the table. We do have a blade pass, but there's no alarm there, and the blade pass wouldn't generate all the harmonics that we have. It would just generate one. And rotor bar is a much higher frequency. You might have 48 or 52 rotor bars, and it'll place it in a very high frequency range, and it'll have sidebands. So it doesn't fit the picture that we looked at for the data we took. So we can eliminate those three specific faults, and if it's not applicable, we can throw those out too. And the one that's not applicable in this case is the natural frequency, and we'll throw that away. Natural frequencies would not produce a series of peaks like that. It would be virtually impossible for that to happen. So we can take that off the table. What's left, we have offset misalignment, we have mechanical looseness type B, and a mechanical looseness type C. Okay, alignment offset, you're going to have an alignment problem across the coupling. Looseness type B usually shows up at 2 times RPM or fractions of running speed, and it's usually a cracked pillow block housing or something like that that's causing the issue. Type C is looseness on the shaft, either on the shaft or in the housing, where there's physical fretting damage to the bearing inner race or outer race. Okay, but we're going to check all those out. So when we go to the next round, so we've gone through the frequency, dominant frequency response, dominant directional grouping. Now we go and see what we should do for each of the individual tiles that are left over. And the first one is phase analysis, okay, for the offset misalignment type fault, and we're going to take a look at that. Next, we're going to look at the time waveforms and see if they figure into the situation. Here's the phase diagnostic checklist. Our red little bubbles on here are my radial type faults and phase relationships. The yellow ones are my axial faults and their phase relationships. So here I have unbalance, eccentricity, and such in the motor and the pump. I have bent shaft, cocked bearings, misaligned coupling, and so forth in this in the yellow blocks and cocked bearings. So let's check them all just in case. We have probable unbalanced response. That is a synchronous fault, and it will not produce multiples. So it's probably not an unbalance or eccentricity problem. We can check for overhung rotor unbalance. That would produce a 1 or 2 times response in the axial direction. We don't have axial response as a key contributor for this one. We're going to check for bent shaft. Those were eliminated because everything's in phase in the axial direction. Everything was looking good. So misalignment across the coupling. In the vertical axis, it looks good. They're in phase. Horizontal, they're in phase. Axial, they're in phase. So we can eliminate this off the table because we don't have a misalignment problem. I can keep going. Check for cock bearings. It's always prudent to look at everything, and they're all in phase, and it looks okay. I don't have any software testing for this one. It wasn't in that category anyway. So the only thing I can take off the harmonic category is the offset misalignment, which was what I was trying to prove in the first place. The recommended diagnostic for the 2 looseness problems is a time waveform. So we're going to take a peek at that and see if there's any signature that kind of matches up. The looseness type B, and I mentioned it a lot of times 2 times RPM is the dominant peak. It doesn't have a whole lot of harmonics like we've seen. So this was 1 through 6 harmonics, and it doesn't match the looseness signature too well. So we could probably take that one off the table. The mechanical looseness type C, also a time waveform. Let's see what we can do with that. It shows up as kind of a random harmonic response. So you see all the different frequencies lining up, the 1 through 6, but you also see a noise floor underneath that. So the noise floor is this random response of the shaft moving and chattering inside the clearances of the bearing. So this looks like it's a highly probable condition, especially when you say there's numerous 1 times RPM harmonics in the spectrum and typically produces a raised noise floor from the transient nature of the impact forcing function. So it's very likely a looseness type problem. Okay. So what have we done? We've found our faults and we've logically sorted to probable root cause. And in the case we have here, it's mechanical looseness type C, which is the looseness condition of the outer race or the inner race of the bearing on the shaft or in the housing.